Okay, welcome back in our study of differential equations. Um, we've looked at what? We've looked at how we can use differential equations to model some physical properties. We've learned how to solve these differential equations, the techniques for solving a separable linear differential equation. Now we're going to look at a few things when we might run into problems. So we understand what a differential equation is. We understand a solution is a function. Let's look at some of our techniques, though, and see when they break down, we have other things we could do also. As I said, if you take second year of college calculus, you'll have a whole semester called DiffEqs. So there's lots of techniques. We're going to show you two more before we finish this chapter. The first one we're going to call slope fields, which I think is a better name. I notice your book is calling them directional fields. Directional. Directional. My handwriting isn't really this bad. I just have to write on a slope surface. So it really makes it hard. Anyway, I like to use the word slope fields because I think you'll remember it better. Okay, so remember what I want to do when I solve a differential equation. First thing I want to do is separate, correct? So here's a differential equation. Let's separate. Well, I'm going to say dy is equal to x plus y dx. Wait a minute. How do I get the y's over here? Wait a minute. Let's see if I x dx plus y dx. Could I divide by y? Anyway, I'm struggling here to show you can't separate. That's why I can't separate. So this is not a separable differential equation. Well, what can I do? I need some kind of different method. That's why I say techniques for solving difficult. What's difficult about this one? Can't separate it. Okay, so here we go. I'm going to look at this thing again. I'm going to look at this equation kind of a different way. And remember what dy dx means. It's the slope of the tangent line. Slope. That's what the slope of tangent is equal to x plus y. Okay, so what I'm going to do is let's plot little tangent lines. I'm going to pick a grid of points. My red points are x's, y points are black. Sorry, my x points are red, y points are black. When x is minus 2, y is minus 2, well, let's see, minus 2 plus minus 2 is minus 4. Minus 1 plus minus 2 is minus 3. 0 and 2 is minus 2, and I'm just kind of filling this thing out. Minus 2 minus 1 is minus 3. Minus 2 minus 1, 0. This is minus 2 minus 1. There's a pattern here. You can kind of see. 1 minus 2, that's minus 1. 0, 1, 2. Okay? What do these numbers mean? What are the blue numbers? That means in the xy plane, when x is equal to minus 2 and y is equal to minus 2, the slope of the tangent line is minus 4. Okay? And as I say here, these are slopes of little tangent lines in the xy field. That's why I think calling it a slope field makes so much sense. Okay, well, what do we do with this? Well, we have this here. This is going to take a little while. Maybe I should, I'll do part of this and then I'll probably stop the, okay, what do we got? We got minus 1, minus 2, 1, 2, 1, minus 1, minus 2, 0. Okay, so at minus 2, the slope is minus 4. So I'll try to draw these. That slope I just drew there was minus 4. And I guess I'm going to have a grid here. Maybe I should just It's kind of a 4x4 grid, right? And each one of these points, I'm going to draw a little tangent line. -2, -2. So I walk across X, and it gets a little bit less steep, okay? A little bit less steep, -2, and then a -1. At -1, it's going to go at -3. These are parallel here. These look parallel. These are at 0. Let's see. At -1, 0, this is -1. And then, oh, look at this. This goes horizontal. I go across one, y is equal to 0. And I get -2, -1, 0, +1. It's a little hard to see now. Okay, these, I'm drawing little tangent lines. I'll draw you better. I'll show you a pre-printed versions a little better. When y is equal to 1, this is equal to -1. This is horizontal tangent. This is +1. This is +2. Okay? All right, well, what does this look like now? Whew. Well, it depends on, so I get little tangent lines. Now, remember, if I draw in y, when you try to solve this equation, what are you trying to find? Y as a function of x, right? I'm trying to find that. So if I drew one in here like this, if I had a point here, I might get a curve. The curve has to follow the tangent lines. Okay, remember? These things are tangent. So for instance here, if I had a point here, so if I'm going to get different curves depending on where I start. If I start here, I get a curve that follows these tangent lines. And I like to say it's kind of like you're driving on a highway. You cannot go through the guardrails. The guardrails is the slope field. Here's another one here. I could maybe draw in a curve. It can't go through that. It's flat right there, right? And then perhaps it goes out like this. And then on this side, it's going to go up like that. What am I drawing? Potential y is equal to a function of x. The red curve could be, this is a graphical way. A slope field is a graphical mechanism for obtaining an approximation to the solution of this differential equation. Why is there two potential answers? Depending on where I start. Remember, this gives me, I need to start somewhere. If I start here, I might get something like the other curve. That could be position 1. Position 2, I might get this kind of solution curve. Okay, let me stop the film, stop this, and I will pull out a problem with a better picture that we can draw on. Welcome back to our study of slope fields. And this would be the type of kind of question you might get where you're actually given a slope field and you're asked to draw us, what are we asked to draw here? A solution curve that passes through the point 1, 0.5. I guess this is 1. And this right here is 0.5, so we're kind of right here. Remember, what are these? These are little tangent lines. So I can never draw, a solution curve never cuts through those things, because then that line would not be a tangent. So when I view this, I always talk about we're driving on a road. We're driving on a road and we're using these things as guardrails. And I'm kind of carefully drawing in my solution curve. And it's, okay. So what's this? When I say it's a solution, this is a y equals function of x that would satisfy this curve. Okay, that's the differential equation. Slope field. This one I can actually solve. Y is supposed to be the natural log, but anyway, there we go. This is a solution curve. Solution curve. Let's look at another type of problem for a slope field. Okay, here again, we could draw on a solution curve, and I'd pick a point, depending on where you pick. Well, let's say they give me this as the initial point. Well, I can go to the right, but I can't cut through any of these guardrails, right? And it looks to me like my solution is kind of a circle. It looks like a circle. My solution to whatever, I'm not even showing you the differential equation. This gives me what? I don't have an algebraic solution to the differential equation. I don't have a numeric solution for the differential equation. But what I have is a graphical solution of the differential equation. Okay, I could tell you, hey, that's a max, that's a min. All right, let's look at another problem. Here we go. Is this, oh, looks like I got too much of this. Hold on. Okay, here we go. There's another type of question. They're a little hard to ask questions, but here, okay, here they give you which particular solution of this differential equation. Now, this is kind of interesting because it means I need to have a knowledge of functions. Okay, so I start right to left. Y equal 1 over x. Well, 1 over x, oh, this could be difficult. 1 over x kind of looks like this, right? Cuts right through it, so that can't be right. That's not right. I do this by a process of elimination. Y equal the natural log. Well, natural log is something that looks like this. Again, it's cutting right through some guardrails right here. That's a horizontal tangent. That can't be right. No. Which, how about y equal e to the x? Well, what's e to the x look like? That's e to the x kind of looks like that, right? And never goes to z. That looks like a pretty darn good candidate. That looks pretty good. What's e to the minus e to the x look like? That looks like this. That's not right. E to the x squared, what does that look like? Well, that's more like, that's even. It's an even function. That's not right either. So there you go. There's my answer, y to the ex. Okay, another type of slope field problem. Here we go. They give me a slope field. They give me the slope field. They don't ask me for the solution. They ask me which differential equation matches this slope field. Well, first thing I see, I kind of look, what I do is I look in the extremes and I look for horizontal tangents. In this particular case, it looks like I've got a horizontal tangent when x is equal to 2 or something. Not at x equal to 0, so it can't be this one. It could be B or C. Can't be y. Notice D. D tells me the derivative, the slope is just dependent on y. Clearly, it changes as I go across x. Can't be that one. Can't be x plus y. The slope looks like it only changes with x. It doesn't change with y. Notice if I hold x constant and I walk down y, it doesn't change. So it's not a function of y. So it's one of these two right here. Let's look at that a little carefully and see if we can figure out which it might be. Is it 2x minus 4? So at x equal to 0, is it negative? At x equal to 0, B says it's negative 4. And it looks at, and y says, C says it's positive 4. So clearly, because of that, the answer is B. Why? How did I deduce that? There's a horizontal tangent at x equal to 2, and at x equal to 0, I've got a negative slope at x equal to 0. Okay, so B's the answer. See if I got another one of these goodies. No, that's it. Okay, so again, we looked at a slope field. Slope field gives us a graphical way to get a solution to a differential equation, even when we don't have the ability to separate it or integrate it. Looks like I'm running out of time here, so I'll probably cut another video for the next solution we have for difficult differential equations.